Guess if I tap water, it was a joke. Just being a jerk, Max. I'm sorry.
So to add to your potential water intake, I actually have a container of ice over there. So if you want, yeah, we're up in the game.
Oh yeah.
Okay, so we have ice, and there's this little cup there. Don't reach in and grab the ice out, please. I know your hands have been. And then there's some more lemons that are sliced up over there. So if you want to avail yourself, because eventually I'm just going to ban water bottles in my room.
What are you talking about?
Yeah.
What
Yeah.
water?
I'm just going to
When are you going to sell your water?
Well, yeah. When are you?
Yeah, when are
those
yours
bottles?
coming in?
They're supposed to be like this week.
Yeah.
So,
Well, there's not much of this week left.
well, I know, but I met with them Tuesday after school, and she said, hey, they're supposed to be in this week. Of course, they were supposed to be in last week, too.
Can we put in a
But I mean,
pre-order?
once
Can we put in a pre-order?
Yeah.
Put in a complaint. Maybe they'll give you a discount.
once those come in, though, I'm getting rid of the.
But then
I'm
you
getting
can
rid of
charge the
plastic.
same price when you get them, so that's more money to the soda man. Yes, discount for him, none for us. That's the way it's going. Just the most. Why are you just squeezing the lemon in
Okay.
there instead of shoving it in the lemon water? But you put the lemon in the water. Cut it in half and stick it.
Slice the lemon.
Where's the knife? You got
Thanks. I'm glad this is
He's just
being
got a
recorded.
big lemon. He just got a big lemon. He's just like.
Okay, anyway.
It's gone.
I feel great. All right. So to kind of get you an idea of how we actually use these equations, so we're going to do a simple demonstration of how you can use these equations to figure out a whole bunch of stuff. So we've got the basic fan cart, okay, right? Familiar with this one. So I'll take it over here. I just have a little footage over here. So great. I need you to do a little timing. Okay. So I'm going to get this up to full speed, right? And then I'm going to let go of it. So what are some things that we could measure?
Time. Distance.
Time, distance,
Velocity.
velocity. Now how would we measure velocity?
The distance over the time.
Distance over the time. Peanut butter crackers?
Want one?
I'll put crackers. I got to talk. Okay. So that's the weirdest exchange I think I've ever had at this time. And that's saying a lot after 25 years. Okay. So here's the deal. Could we, let's say it's going to travel 1 meter. Okay? And let's say that it took, I don't know, 2 seconds. Make up a number. So to get the velocity, could I take 1 meter and divide that by 2 seconds and go, it's traveling a half a meter per second?
If it's constant.
Yes.
Yes. Everybody cool with that? No one should be cool with that. All of you should be going, oh my God, no, Mr. Burkamp, because what's the initial velocity of the cart? Zero. What is it doing? Speeding up. Do you have constant velocity? No. So can you take distance and divide it by time to get velocity?
You said it was going to be a full speed before you let go.
No, the fan is up to full speed. Okay, the fan itself is up to full speed. This isn't up to full speed. This is starting at 0. So that way I want it up to full speed, so I'm providing a constant force.
Gotcha.
Yes, this is starting at rest. Okay? So if you ever, on the next 3 assignments, find yourself taking distance and dividing it by time to get velocity, stop. Okay? Get help. Call the velocity, call the distance over time helpline and go, I'm addicted to this equation and I need help. Don't use it. Now, I can measure time. I can measure distance. Do you think it would be very easy to measure acceleration? No. Okay, tough to measure acceleration. Even tough to measure velocity. Why is it going to be tough to measure velocity? It's continuously changing. Okay, so the only thing that we can really measure in this whole deal are 2 things. We can measure the distance it's going to travel, which is going to be 1 meter, and we can measure time. But then we can do a whole bunch of stuff with this. Now, if we're clever, and we are, what do you think the initial velocity of the cart should be?
0.
0. Oh, because then a whole bunch of things up there on that board drop out, because the initial velocity is going to be 0. That's why I don't want it moving at the beginning. Okay? So, now, Nick, you ready to time? So I want to go from here. I'll tell you when I'm going to let go, and then you stop it when the front of that cart crosses 1 meter.
The front of it?
Yep, front.
Okay.
So we're going front to front. Okay, you ready?
Do you go 3, 2, 1?
Yeah, we're going to go 3, 2, 1, then I'm going to let go. Ready? 3, 2, 1, go.
Oh, no. You said 3, 2, 1, then let go.
And that's what I did. I went 3, 2, 1, go.
You said go. I thought you were going 3, 2, 1. Okay.
Listen for go.
Okay, I'll listen for go.
3, 2, 1, go.
Got it.
Okay. What'd you get?
Just turn it around.
250, exactly?
Yep.
That's weird. First block got the exact same time.
Oh, wow.
It was exactly
Must be precise.
Yes, it was exactly yeah, that's weird. Okay. All right. So, here's what we've got.
Shake it around a bunch.
So, here's the cart, right? Now, we know it traveled exactly 1 meter. That was kind of cool, right? And the time was exactly 2.50 seconds. Okay? Exactly 2.5 seconds. So, knowing that information, what can I figure out? Can I find the acceleration?
Yes.
Well, look. What's my initial velocity?
0.
0. So this whole thing drops out, right? Do I know distance?
Yeah.
Yeah.
Yes.
Do I know time?
Yep.
Yes.
I can find my
Acceleration.
acceleration. Oh, that's kind of cool, right? Now, could I find anything out of here?
No, because you need to have.
final velocity in that.
Well, you could find it.
Do I know the distance?
Yeah.
Do I know the time?
Yes.
Oh, you
Do I know the initial velocity?
Yes.
Could I find my final velocity that way?
Yes.
Yes. Okay? So I can find my final velocity here. I can find my acceleration here. Can I get anything out of the first equation?
No,
Why not?
you don't know acceleration or your
Yeah, I have
final,
two unknowns. I don't know acceleration and I don't know
final velocity.
final velocity. But I do know V naught. But I have two unknowns with one equation. Can't do anything with this. Cool equation, I just can't do anything with it. Now, what would the position time graph look like for this? 3. What would the position time graph look like from when I let go of it until you hit the 1 meter mark?
It would,
Like
I think.
that? So, upper lip, lower lip, middle lip.
Oh,
Upper lip? This one?
yeah,
Why?
because it's not like still like it's like speeding up and then it's starting to go like constant.
Okay. Great.
Plateaus out. So
Yeah,
it's
that's a good word.
Yeah,
There you
so
go.
it's the upper. Is it,
Yeah, but
you're looking
on the
at song?
position time graph,
Huh?
I said, but that wouldn't be, horizontal doesn't mean constant velocity on position time graph.
Well, the bottom one would be, like the slope is so high, like it wouldn't be like.
But you don't know what the scale is. We're just
Oh,
talking
we're not,
general
okay,
shape.
okay.
But I think it's the bottom one because it started out slow and then got faster as it
Yeah.
moved along time.
Oh yeah.
Because the
I know.
acceleration
then the-
and velocity we're both at the same sign, a positive.
Because the upper lip would mean what?
It started off fast.
It
then
started
went
off
slow.
really, really fast and then it slowed down as it
Stop.
got towards the end. Is that what happened? No.
It'd be cool.
It would be cool. I'd be like a rocket and then it like hit the air brakes and started to slow down. So, Vonda, what about the middle of the lip?
It wasn't constant.
Ah, can't be the middle of the lip, right? So that leaves us with the
Bottom.
bottom lip. So, you were hip to the bottom lip early. Okay, why?
Take a swig from that.
Start calling you
It's in
peanut
polite
butter.
to- it's in polite to talk.
Peanut butter? What?
All right.
Why the bottom lip?
It starts out slow,
Yeah.
but then speeds up.
Yeah, and the slope of the position time graph gives you velocity. So we're starting slow and we're going faster and faster and faster. Okay, that's kind of cool. All right, so let's settle on that one. Okay, that's kind of cool. Now, what about the velocity time graph? Mary, what would the velocity time graph look like?
Like a straight line.
Kind of a straight line, but yet kind of not? Or
A straight line.
a straight line?
Yeah. A positive.
Like that?
Yeah,
Pretty boring.
yeah, that's okay.
I teach physics, I'm used to that. Okay. Pretty boring, but that's okay. So, what do you do? I teach physics. Oh, really? Okay. So, here's the deal. On this velocity time graph, why is it a straight sloping line? And this line is right.
Acceleration.
Yeah, well, uniform acceleration, because look at F equals ma. Are we changing the mass? Was the force the same?
Yes.
Yeah, because that's why I waited until the fan got up to full speed to let go of it. So if I have a constant force and a constant mass, I have to have constant acceleration. Okay, so the slope of this line. Okay, well, cool. Now, it traveled 1 meter. So how does that 1 meter play into this velocity time graph?
Displacement.
Which is also going to equal
Area.
Good. So if I go out here to 2.5 meters, right, this area here, right, would have a value of 1 meter because that's how far it went. Okay? And I got my time of 2.5 seconds because that's how long it took for it to travel that distance. So if I go here, I know the time and I know the displacement. So I get my acceleration. So how is that acceleration going to play out on this velocity time graph?
Slow.
It's going to be the slope of the line, okay? And it's not the hypotenuse, okay? That's just going to be the slope of the line. So, Felix, solve this for acceleration.
Minus
No,
0.
all that goes away.
Okay. Times 2.
Yep.
And then take the square root.
Oh,
or
no.
divide t and then do the square root.
No. Because the only thing that's squared is t. This a isn't squared. I'm just trying to get a by itself. So if I multiply by 2, let's go with your steps, right? So I got 2d equals at squared. But only the t is squared.
Just divide by t squared.
Beautiful. I don't want to take the square root of anything. I'm just going to divide by t squared. Because here's the deal. If you try and do the square root, you're going to get some completely jacked up units that are not meters per second squared. Because it's only that acceleration, or that time that gets squared, not the acceleration. Okay. Now, so we said we've got 2d over t squared is going to give you my acceleration. So I got 2 times, so sort of take a calculator, take 2 times 1 meter. If you punch that into your calculator, I'm going to hurt you. And then, I was just checking, really, Mr. Campbell. Okay? So take 2 and divide it by 2.5 squared.
0.32 meters per second squared.
0.32 meters per second squared. So, on the velocity time graph, what does that get me? Mike, how does that 0.32 play out on this velocity time graph?
For every 0.32 meters. Oh wait, no.
You're good. Reverse it.
Okay.
For every second,
We go 0.32 meters.
beautiful, okay? That's going to be the slope of that line, okay? Because Michael approached this and he says, look, this is what the slope means. For every second that goes by, this is how much my velocity changes. That's what that means. So at the end of 1 second, he knew he was going 0.32 meters per second. At the end of 2 seconds, we were going
.64 meters.
0.64, okay? So, this is gonna give me that final velocity. I'm out here at 2.5 seconds. So, there's two ways we can find this final velocity. One is, now that we know the slope of the line, we could go v equals v naught plus at. True? We know the initial velocity.
Yeah.
You know the acceleration.
Yes.
We know the time.
Yes.
Yeah, so that's just going to be 0 plus 0.32 meters per second squared times 2.5. So somebody take 0.32 times 2.5.
0.8.
What'd you get?
0.8.
Exactly?
Yes.
0.80 meters per second. Now, this is cool, right? Got 0.8 meters per second. Here's what's important out of this. Notice that this is a linear function because it's just acceleration times time. So here's my question. If at 2.5 seconds I was going 0.8 meters per second and my position time graph looks something like this. So if I come out here to 2.5 seconds, how does 0.8 meters per second play into that position time graph?
It's the slope.
Yeah, that's the slope of the instantaneous velocity. Get a water bottle tap for that one.
Got ice in it.
Oh, okay.
How am I supposed to get the ice out?
My bad. I was just,
Peanut butter?
No.
Okay. So, if I came out here at 2.5 seconds and drew a tangent line, guess what? That would be the slope of the tangent line. Now, here's the $1,000,000 question. What if I went to half the time in 1.25 seconds? What would the slope of the tangent line be there? Shively.
4 times less.
It is going to be less, right?
Yeah,
But why 4?
because it's like quadratic instead of like the other one.
No. But remember, you're throwing quadratic into something different. Okay?
Okay.
You're throwing position into this. Here's the deal. What does the slope of a position time graph give you?
Velocity.
So here's my point. You got to figure out what's linear and what's quadratic. So if I came here to 1.25 seconds, so here's the deal. If I'm traveling 0.8 meters per second on a linear function at 2.5 seconds, if I go to half the time, what should my velocity be?
0.4.
Should be 0.4 because this is a linear function, right? So this should be 0.40 meters per second. So if I go to this and draw the tangent line, what's the slope going to be?
0.4.
Yeah, because that's my instantaneous velocity. Okay, so don't throw position into this because I'm just asking, hey, what's the velocity at this point? Okay, so the slope here is going to be 0.4. The slope here is going to be 0.8. So this is how this graph plays out with this graph. Okay, don't confuse what's quadratic and what's a linear function. Okay, cool with this. All right. Now, here's the disadvantage of finding your final velocity this way. The disadvantage of this is that if you messed up your acceleration, you've messed up your final velocity. Okay, that's just the reality of it. So here's what you want to look at, is that we could use distance equals 1/2 v plus v naught time. The advantage of this is I know my initial velocity is 0, I measure time and I measure distance. Generally what you want to try and do is use values that are given you in the problem as long as you can. So the advantage of this is that I don't have to base it upon my acceleration. Because if I've screwed up my acceleration, I've screwed up my final velocity. The disadvantage of this is that the algebra is a little bit dodgier, but it isn't bad. Oh, hey, multiply by 2. I got 2d equals v plus v naught times time. Okay, well that's pretty simple. I want to get v naught by itself. That's 0. So basically, I just have to divide by time. So somebody take 2 times 1 meter and divide that by 2.5 seconds. What'd you get?
0.8.
Yeah, you still get 0.80 meters per second. So here's the deal. You can't have one set of equation producing a final velocity of 0.8 and another one producing a final velocity of like 1. Something has gone horribly wrong. So the advantage of this is that you're not basing it upon a potentially screwed up acceleration. So if you can use the numbers that you're given, as long as you can, that's a cool deal. Okay? Got it? Great. Okay. Now, here's the last of the equation. Then it's v squared equals v naught squared plus 2ad. Now, where this equation comes from is the idea of conservation of energy. And it deals with potential energy and kinetic energy. So potential energy is stored energy. Usually talk about gravitational potential energy. Like if I hold Gary the golf ball up above the ground, he's got potential energy. When I let go, that automatically starts to change into kinetic energy. So about the first week in December, once we've studied potential and kinetic energy, you all will derive this equation, okay? All it comes from is energy is conserved in terms of potential and kinetic energy, okay? You will eventually, on one of your last assignments, prove where this equation comes from. But here's what's important. If you look at this one and compare it to v equals v naught plus at and distance equals 1/2 v plus v naught time and distance equals 1/2 at squared plus v naught time. What's different from this equation from the other three?
The velocities are squared.
No. What's missing in here that's here and everything else? Time. Okay? This is the only equation that does not involve time. So if you ever get a problem that doesn't involve time, go to this equation. Now, over the years, and this goes back probably 6-7 years, for whatever reason, this is known as that equation. Okay? So if you go to any of my former classes and go, hey, we learned that equation today, they're going to know exactly what you talk about. So this is, for whatever reason, this is the only one that is known as that equation. So it's like, hey, what equation doesn't involve time? That equation. Okay, everybody will know exactly what you're talking about. So if I talk about that equation, this is the one. Now, the other thing is that this is the other one that only has everything squared, okay, in terms of squaring their velocities. Okay, the other ones are just, you know, v naught, all that good stuff, right? And then you've got an acceleration and distance. So here's how this one plays out. So you'd have something like this. Here's the carrot car, and you know, like let's say they're designing a highway. And you know the initial velocity of the car when it comes off the ramp is about 4 meters per second. So imagine a car coming off the ramp and you've got to build the acceleration lane. Then, you know, the final velocity of the car might be 20 meters per second. And you know that typically cars on average will have an acceleration of about 5 meters per second squared. Okay? Now if you really press down on the gas pedal, you might get like 8 or 9 meters per second squared. So this is a fairly decent acceleration. Faster than probably what grandma has, but slower than, you know, guys that drive souped up cars. So that's kind of an average acceleration. So here's what I want to know. These cars hit this acceleration lane at 4 meters per second. Here's my average acceleration. When they merge into traffic, they need to be going 20 meters per second. So what I need to know is how much of this do I need to build to allow this to happen? Do I need 5 meters? Do I need a mile? What does this length need to be? So what is not here?
Time.
Time. So right away, you're going to go to that equation. Now, here's what typically happens. Okay? I'm going to change this a little bit. Let's say instead of giving you the acceleration, let's say I gave you the distance of 200 meters. Let's just say. And then ask you to find the acceleration. This is what you all are tempted to do. You're tempted to go, oh, I'll take 200 meters and divide that by like 4 meters per second and I'll get a time. Okay? If you don't have a time in a problem, whatever you do, do not ever find time by taking distance and dividing it by a velocity, okay? Don't ever, ever, ever find time this way on an accelerated motion problem. It won't work, okay? Again, I cannot emphasize this enough. Do not find a time by taking a distance and dividing it by a velocity, because you're accelerating and the velocity is always changing. So again, if you find yourself trying to use this to find time, stop. Don't. Okay? Don't do it. And you all sit there and go, oh, Mr. Burkamp, we won't do that. Lie. Lie. Because every class says, we won't do that, and then somebody does it. Okay. So, how can I find the length of road that I need to build?
That equation.
That equation. Oh, that equation. So I've got v squared equals v naught squared plus 2ad. Now, let me point out one thing. Even though this isn't what you're going to do in this particular problem, if you have to solve for v, and you go, this isn't how you're going to work this problem, but I want to point out one thing. So if you go v naught squared plus 2ad, and you got the square root of that because you're trying to get the final velocity by itself, do not do this. Do not look in this and go, oh, the square root of v naught squared is v naught, so that's just v naught plus the square root of 2ad. Do not do this, okay? Do not do this. You cannot take out just the square root of that because it's added together. They're not multiplied together. So if you have to find the final velocity, which you will, don't do this step. You've got to square it, you've got to add it to 2ad, get that number, and then take the square root of everything. Okay? Don't just take this out by itself. It won't work. Okay, so now that we've done that little diversionary problem, and I have an eraser that won't erase. There we go. Weird. Okay. So I need to get distance by itself. McGriddle, what can I do?
Actually, you subtract.
Subtract.
Was that 2a?
Go minus 2a. Shively's waving you off, man. Shively's giving you like, he's waving off the bunt sign, okay?
You're gonna get a d by itself.
I'm trying to get a d by itself. It's like bingo. Can I buy a d? It's like physics equation bingo. Oh, he's busting out the
I
glasses.
can't see this other number. Is that a 2 something?
Okay, this is.
Okay, yeah.
Your handwriting.
Okay, look, it's written on your equation
It is.
sheet. It isn't like this is like a scribe and I'm writing down a message from the oracle.
You're gonna divide by the 2a first.
Eli, no. Eli.
Subtract.
How about v squared minus v naught squared equals 2ad? Then what?
Then divide by 2a.
Then divide by 2a. Are we cool with that action? Everybody cool?
Yeah.
I blame the new math books you guys have. Okay. So,
You're bad, man.
before we do anything, do you think my displacement is going to be a positive or negative number?
Probably a positive,
Why?
because you're going from 4 to 20.
Because the final's bigger.
You're going.
Well, number one, my final is bigger than my initial, right? And if you were to look on a velocity time graph, you're going to start at 4, you're going to end up at 20, and so this area underneath is going to be a positive number. So if you do this and you get a negative number, you go, wow, something has gone horribly wrong. Okay? And again, do not get wrapped up into just playing the answer game and going, oh, what equation do I pick? And then I'll put in the number. It's going to be a train wreck. Okay? You have to look at this and go, hey, does my answer even make sense? Now, then I can take 20 meters per second and square that minus 4 meters per second and square that. And then I'm going to divide that by 2 times 5 meters per second squared. So somebody take 400 minus 16 divided by 10. 18.4?
38.4 maybe?
Yes.
That's 400 minus, yeah. Okay, 38.4. Okay?
No.
Which is about half the length of the football field. Okay? So that's about how long I need to build that acceleration line. Now, what would happen if I knew cars accelerated at a slower rate? Let's say cars are only accelerating at 4 meters per second squared. What would that do to this length?
It would increase.
Yeah, so I'd have to build it longer. Okay? All right. Cool with this. So there's the last equation. Now, we need to tie a whole bunch of things together into one idea. So speaking of accelerated cars, so here's the carrot car. We're going to let it start at rest. And we're going to have an acceleration of 4 meters per second squared. And we're going to look at times 1. Okay, so imagine this. We've got the carrot car, and it's at rest. And we know the carrot car is going to accelerate uniformly at 4 meters per second squared. I want to figure out how far it goes at the end of 1 second, 2 seconds, 3 seconds, and 4 seconds. And then I also want to figure out how fast it's going at the end of 1 second, 2 seconds, 3 seconds, 4 seconds. Okay? Pretty simple. So, let's start with this. What's my velocity time graph going to look like? Ethan, what's my velocity time graph going to look like? So, let me kind of erase this. So, let me erase this. Why will it? That's the most weird thing.
Just draw white over it.
White pen.
Okay, this is possessed. I think somebody put a jack-o'-lantern up on my. Okay.
So what do you wish for Halloween?
Yeah. Okay. We've had this discussion. All right. So here's my velocity time graph. So where is it going to start?
It's gonna start at 0
And go.
up, and then positive sloping down.
And what's the value of that slope?
4 meters per second squared.
Okay. Right? 4 meters per second squared. So now there's a couple ways you can figure out that velocity. One option is that you're going to the store and mom's going to give you $4 per second, okay, to spend. So you walk in and you have no money. At the end of 1 second, how fast are you going? 4 meters per second. Mom's giving you $4. At the end of 2 seconds, you're going to be at 8. 3, you're going to be at 12. 4, you're going to be at 16. So that's about as simple as it gets, because this is a simple linear acceleration. So you're going to be going 4 meters per second, 8 meters per second, 12 meters per second, 16 meters per second. It's not bad. At the end of 4 seconds, you've got $16. That's not bad. Okay. Now, but that's just if you look at the slope and realize, oh, this is what we've got. Now, what if you go, but Mr. Burkamp, we've got these cool equations. Yes, you do. You have very cool equations. So one option is that you can go, oh, okay. To get this velocity, we can go v equals v naught plus at. You know the initial velocity?
Yeah.
Yeah.
0.
You know the acceleration?
4.
Yes.
Yep. All you're doing is plugging in time. So this is like a y-intercept thing. That's all it is. It's a y-intercept. What's my y-intercept?
0.
Why?
Because you start with 0 velocities.
Yeah, I'm not moving when I start. So all this is a y-intercept. Now, here's what's important. This is a linear function because it's just acceleration times time. It's not time squared, it isn't time cubed, there's no square roots, there's nothing weird about this deal. It's just a simple acceleration times time. It is the poster child of a linear graph. because it's just acceleration times time. Now, I want to figure out how far it's gone at the end of 1 second. Could I just take 1 second and multiply that by 4 meters per second and go, oh, it went 4 meters? Hunter?
Yes, sir.
I could. Everybody cool with that idea?
No,
No, none of you should be
No.
cool with this idea.
it's not constant velocity.
It's not constant velocity. What's the only time this thing is going 4 meters per second?
At 1
At
second.
exactly 1 second. At a half a second, how fast was it going? 2 meters per second. Okay? The only time you can take 4 meters per second times 1 second to get the distance is if you have,
Constant.
is this constant velocity?
No.
No! Now, but again, you're going to Mr. Burkamp. I like triangles. This looks like a triangle. Yes, it does. Do you know the base of this triangle?
Yes,
The base of that triangle is?
1 second.
What's the height of that triangle? 4 meters per second. Now, can I take 4 meters per second times 1 second and then divide that by 2?
Yeah.
Yes.
1/2 base times height, right? And I would get 2 meters. But here's the downfall. That's dependent upon a final velocity of 4 meters per second. If that 4 meters per second is wrong, guess what? That's going to be wrong. You lose. Now, what I would recommend is I'd look at distance equals 1/2 AT squared plus V naught time. I would recommend this because this is not dependent upon a final velocity. This is only dependent upon the information you were given in the problem. I don't have to worry about the V naught T because that goes away. Now here's what's important. In terms of velocity, it's just acceleration times time. It's a linear function. But when you're talking about displacement, notice that this is 1/2 AT squared. Okay? So as soon as you see 1/2 AT squared, guess what? It becomes a quadratic function, or an exponential, depending upon how you want to say it. So as soon as you see t squared, I know this cannot be a linear function. But if it's just acceleration times time, then it is a linear function. Okay? So as soon as you see anything squared, when you graph it, it cannot be linear. Now, you're going to get the same answer here, because what you're going to do is you're going to come in here and you can go, okay, distance is 1/2 AT squared plus V naught time. International sign for that goes to 0 because I'm starting at rest. Don't have to worry about that. Now, here's the deal. Is my acceleration going to change as the car speeds up? Olivia, is my acceleration going to change as the car speeds up? No. No. No.
No.
Why not?
Because it's going to go the same rate.
Yeah, it's uniform acceleration, right? So my velocity time graph is going to look like this. Same acceleration all the time. So if you want to shortcut this, well, that's 4 meters per second squared. Half of that is 2. And then I can multiply that by 1 second squared and check my math, but I should get 2 meters, which is the exact same area that we calculated when we used the triangle and the final velocity. We get the same answer either way. This is nicer because this is only dependent upon known value. Now, if I take that same 2 meters per second squared and multiply that by 2 seconds squared, now what do I get? 100.
4.0 meters. Oh wait, no, hold on. 8.
8 meters. Why?
Well, because the 2 squared.
Yeah, I got 2 squared, which is 4. 4 times 2 is... Now, here's something that's really important. Notice I doubled the time. Okay? I doubled the time. But what happened to my distance? It quadrupled. Because anytime you double something that's squared, it goes up by a factor of 4. Okay? Now, if this was just acceleration times time, if I doubled the time, it would only go up, it would also double. But because this is time squared, If I double the time, it goes up by a factor of 4. Okay? Now, what if this is like time cubed? Then it would go up by a factor of 8. Because 2 cubed is 8. So if something's cubed, then but that's pretty rare that you can see something like that. Now, if I plug in 3 seconds, what do I get? 18 meters. And then if I plug in 4 seconds, I get 32 meters. So here's the deal. This position time graph is going to be a very much a quadratic function. There's 32, there's 4 seconds. It's actually like this going. Now, again, here's where this becomes a big picture idea. If I come in here at 1 second, and I draw that tangent line, what's the slope of the tangent line going to be at 1 second?
2 meters. Excuse me.
Wanda?
4.
4? You say that with absolutely no confidence whatsoever?
Yeah, I'm just gonna go with 4. I think
4 what?
meters per second.
Why? Your answer is beautiful.
Because it's velocity.
And that's how fast we're going at the end of?
With 1 second?
Yes. So the slope of this line would be 4 meters per second, because that's how fast we're going at the end of 1 second. Now, what's our position? How far did we go at the end of 1 second?
2 meters.
2 meters. But my velocity is 4 meters per second. Now, if I go to 2 seconds, I'm going to be at 8 meters, but the slope of that line is going to be 8 meters per second, because that's how fast I'm going. You go to 3 seconds, you're going to be at 12 meters per second, but you're going to be at 18 meters. Okay? So you have to understand how position time graphs and velocity time graphs relate. So if you can ever figure out what the velocity is at any point, that's what the slope of your tangent line is going to be on your position time graph. Okay? Got it? Good? Okay. So, stop that.
Number 1, got it. One question answer? Change.
Yeah?
Slowing down, speeding up.
Okay. Now, listen to me very, very carefully. On assignments like this, and you're going to have a lot of them, do not answer a single thing on this sheet. Okay? Nothing gets answered on this sheet. You can write on it, you can make notes on it, you can do whatever you want. But I will grade nothing that is answered on this sheet. Absolutely nothing. Even the multiple choice. Do you understand me? I will not look at this sheet to find a single answer. If I want you to answer it on the sheet, I will give you space and I will give you areas to write down the answer. Okay? But if you don't see areas off to the right to write down the answer, you don't answer anything on the sheet. So here's how I want this done. You're going to take yonder sheet of graph paper, or excuse me, your notebook papers, and you're going to come over here about a couple inches, and you're going to draw a line. The little red line that exists on your paper is not far enough. Okay? I want you to come over a couple inches. Now, here's what's going to happen. In this space here is where you will put your answers. Over here is going to be any work that generates those answers. Okay? So, if you look on this assignment, you've got 1 through 6, those are multiple choice. Okay? So you can just sit here and go, okay, 1, 2, 3, 4, 5, 6. Okay? And you're just going to put your answers here. Okay? If you need to do some calculations for those over here, really don't care. Main thing is, this is just multiple choice, not a big deal. Now, the heart and soul of this assignment, and any assignment, is when you get down towards the bottom. So if you look on number 7, it says, can an object move with uniform acceleration and constant velocity at the same time? Explain. So in number 7, you're going to answer number 7, and you're going to write that out. You can spread that out across both lines. You don't have to cram that in right here. You can spread that out. When I talk about uniform acceleration, 0 meters per second squared does not count as uniform acceleration. Okay, that's a non-zero value. So when I'm talking about uniform acceleration, I'm talking about something other than 0, 0.1, 5, negative 1,000, whatever it is. Okay? So 0 meters per second squared does not count as uniform acceleration. Now, here's the main thing that's going to happen on number 8. And I'm going to show you how I want number 8 working. We're going to work number 8 together to make sure everybody knows exactly what I want. So you're going to put number 8, and then here's going to be the answer to number 8. Over here is where you're going to generate the work that answers number 8. So here's the deal. So let me kind of, I doubt this will erase, but we'll try it. Oh, it kind of does that. That's just so weird. Okay, close enough. So I'm going to work it kind of like the full-blown way. You don't have to write down all of this, but I'll show you the minimum of what I want. So if you look at number 8, what information are you given on number 8? Velocity. Which one? There's a big difference. Final. What's my final velocity, Mary?
100 meters per second.
100 meters per second. About a third the speed of sound. Okay. How many significant digits does this have, Mary?
4.
4. 100.0. Okay. 4 significant digits. All right. What else do you know?
Time.
I got a time of
10.0 seconds.
how many significant digits there?
3.
3. What else do you know? You know something else that's important. Well, it's going straight up, but beyond that.
Initial velocity?
What's your initial velocity?
0.
How do you know your initial velocity is 0?
Because it starts.
It's on the launch pad and it's going to start at rest. So if I want this thing already moving, I would have to give you that initial velocity. So I know V naught is going to equal 0. Now, what are you trying to find? Trying to find my acceleration. That's my great unknown. So now, think about this. Before you do any calculations, is your acceleration going to end up being a positive or a negative number?
Positive.
Why?
Because it goes from 0 to 100.
Right? I'm speeding up with positive velocity. Therefore, I have to end up with
Positive acceleration.
Now, if you look on every one of these problems, I can only do one of two things. Either I can make this thing speed up, or I can make it slow down. It is a two-trick pony. Speed up, slow down. If it's speeding up, what do you know about velocity and acceleration? Same sign. If they're slowing down, you're going to have opposite. So read the problem. Okay? Right away, that's the only two things I can make this thing do. So if you know it's speeding up, you know your velocity and acceleration have to have the same sign. If it's slowing down, guess what? They got to have opposite signs. It's as simple as that. Okay? Now, at this point, I need to pick an equation that relates all of this stuff. So what are you going to go with? Maybe a little
V equals V naught plus AT.
plus AT. Now, this is what I do want to see, and I beg of you. The sooner you all embrace this idea of solving equations with variables, the sooner you embrace this idea, the better off you're going to be. You're going to see a deeper understanding of the material, and it's just how science is done. You are not in an Algebra 1 class. Don't write down the unit, or don't write in the numbers and then solve it, okay? It's not going to end well. Trust me, it is not going to end well. So, McGriddle, now that you have your glasses on,
I'm ready.
okay? Let's get acceleration by itself. What are you going to do?
Subtract the V naught.
So I'm going to have V minus V naught, then what? Divide by T. That's going to give you my acceleration, right? I want to see this, okay? You have to realize, I want to see what you're trying to do. I don't want random numbers written down that don't have any units. That means nothing to me. I want to see this process. Now, after you get that done, then you can put in the numbers. Then you can go, oh, okay, that's in my wheelhouse. That's 100 meters per second. Minus 0 divided by 10 seconds. Tori, what units do I get out of this? Meters?
Per second squared.
Are you sure?
Am
I don't know. Are you
Does it
sure?
sound right?
I don't know.
Sure.
You're right. Now, because again, pay attention to the units. It's meters per second divided by second, so you get meters per second squared, otherwise known as
Acceleration.
Now, what I'm going to do is wrong. Do not do what I'm going to do. I'm going to come over here to number 8, and I'm going to write the number 10. And that's it. Why is that horrible?
Significant digits and units.
I don't know what it is. Oh, right. Burkamp wants acceleration. I'll put meters per second squared on the end. Now, is that right?
No.
No, still bad. Why? How many significant digits does 10 have?
3.
That just has 1. If I just write
Oh, wait, I
10
was thinking
without a decimal place, that only has 1 significant digit. How many do I need? 3. So how can I write 10 with 3 significant digits?
0.0.
10.0 meters per second squared. So at a minimum, I want to see this, and I want to see this. Now, here's the next step in this process. So I'm going to kind of start over and clean this up a little bit. So here's your sheet of paper. There's this line. So we said the answer to number 8 was 10.0 meters per second squared. We had the work over here, da-da-da-da. Okay? Now, when you move down to number 9, I want a space in between these. Okay? You have to understand, whenever I give an assignment, I've got 51 of these to grade. If you think I'm going to sort through a bunch of random numbers that I can't figure out, you're nuts. Okay? I have better things to do with my life. So, you're going to have the answer to number 8 and the work that generates it. Leave a space. Some people will actually go in and like shade this in, or they'll draw stars or squiggly lines. You don't have to do that, but I'm just saying some people take this to an extreme. But here's the main thing. Then I want number 9, and then I want the work that generates number 9. Don't put the answer to number 9 up here and then the work for number 9 down here. You want to keep this answer right beside that work. Okay? You want to keep this simple for me because I've got to grade a whole bunch of these. And I'm not going to sort through this to try and find this answer. Then you can go to number 10, leave a space, boom, da-da-da-da-da. Okay? So when in doubt, leave a space. Okay? Leave a space, leave a space, leave a space. Okay. Now, that's on the back side. Yes, there is a back side. Let's talk about number 17. So you got a driver's moving at 20 kilometers per hour, abruptly stops the car in 30 meters, or in 3 meters. So here's the deal. When you read the opening salvo on number 17, what did I not give you? Time. So right away, which equation do you think you're going to use? That equation. Now, you have a velocity in kilometers per hour. What do you think you need to do with kilometers per hour?
Change it to meters per second.
Change it into meters per second. The shortcut is you multiply by and divide by 36. When you do this, notice that 20.0 has 3 significant digits. When you convert that into meters per second, I want a minimum of 3. I actually prefer like 4, then you can round when you get to the end. But when you do these sub-conversions, you want to keep at least the same number of significant digits, if not more, and then you round when you get to the final step. Okay? That's going to be a key thing. Now, when you get to problem like number 11, okay, gal's running at 4 meters per second, she slides into second base. Okay? One of the things I'm going to ask you to do is sketch a velocity time graph. So when you get to that one, if you want to do this on your paper, you can. You don't have to put this on another sheet of paper because I tell you it's just going to be a sketch. So when you get to that, if you have room, you can go, okay, here's my velocity time graph. What's that going to look like? Okay? But pay attention to everything that I want labeled on that graph. So if I just say, hey, make a sketch, this is all you have to do. Now, the other thing that I want on number 11 is that when you look on 11A, it says draw a motion diagram showing at least 2 velocity vectors and an acceleration vector. I'm going to do this so you know exactly what I want. So on number 11A, here's the setup. Here's second base. Here she is sliding in, right? Which direction is her initial velocity vector pointing? Towards the base, right? So we're going to call this V1. As she slides, one of 3 things can happen. The velocity vector gets bigger, the velocity vector gets smaller, the velocity vector stays the same. Smaller. So I'm going to go, okay, here's V2. Okay, I'm going to draw that a little bit smaller there. Okay? Easy peasy, no worries. Now, that's all you have to do. All you're showing is that my velocity vectors are getting smaller. That's all you have to do. That's it. But then you want to draw an acceleration vector. Your acceleration vector can only point in which of 2 directions relative to these velocity vectors. It can either point in the same direction or the opposite direction. Which way is it going to point?
Opposite.
Why?
Velocity.
You're slowing down. So just come down here and go, oh, there's a negative acceleration vector. That's all you have to do for that motion diagram on 11A. Draw a V1, draw a smaller V2, point that acceleration vector in the opposite direction. That's all you have to do. Okay? When in doubt, leave space. That's your mantra. Keep this simple. I've got 51 of these to grade, and my eyes are getting tired in my old age. They're really not, but it's a good excuse. So, but just view this from my perspective. I am not going to sort through this and try and find what you did. You keep this as organized as you possibly can. Okay? Any questions? You're on your own. So,